All right, chapter 25, exercise. So let's talk about these things. Okay, so sources of ATP. Okay, so I'm sure since high school you guys know ATP is the energy currency of the cell. Okay. Okay, so the cellular supply is actually a very small amount, only lasts for a few seconds. Okay, the next chunk of energy comes from creatine. Like they have a phosphate group. The phosphate group goes on ATP. It powers another round of ATP production. But again, that doesn't last much longer, another 5 seconds or so. Okay, short, intense exercise, sprinting, powerlifting. That's about it. Okay, the next round is going to be carbohydrates and fats. Okay, so the sources of glucose. First of all, there's a little bit of glucose inside the cell, but again, a very small amount, and then plasma glucose levels. Okay, plasma glucose levels, and then breaking down of glycogen from the muscle and ultimately from the liver. Okay, and then if you run out all those, gluconeogenesis. Okay, well, actually, the liver glycogen will last for a while. The muscle will not, and then you will use gluconeogenesis to regenerate more sugar. Okay, all right. Okay, so okay, so we'll start here. Okay, so glucose is in the bloodstream, either directly absorbed from the intestines or from breakdown of glycogen in the liver. Okay, fatty acids flow around your bloodstream from either adipose tissue and ultimately from your diet. Okay, okay, so okay, when you're resting, the muscle builds up glycogen, a little bit of glycogen. Okay, when you exercise, you burn the glycogen. Okay, and you make ATP. Okay, that's anaerobic. The rest of the burning is aerobic. Okay, and then you generate a large amount of ATP. Okay, phosphocreatine (PCR) can also power ATP production. Okay, and then you get contraction relaxation. Okay, so fatty acids. This is kind of important, so I'm gonna point this out in a couple places. Fatty acids make acetyl-CoA. Acetyl-CoA is only requires oxygen. So this requires oxygen. So fatty acids only can function when you're breathing adequate amounts of oxygen. Okay? Sugars you can still burn without oxygen. Okay? Which is important. Okay. Okay. Aerobic metabolism, again, you learned this earlier. Aerobic metabolism requires oxygen, is much more efficient. It generates about 30 to 32 ATP per glucose. Okay, it is used for long-term endurance exercise. When you're long-term endurance exercise means you're getting enough oxygen. So you can burn aerobically. Anaerobic metabolism is faster. It's 5 times faster. So it's a lot faster. It is less efficient. And it generates lactic acid or lactate. Okay. Okay. So the first uh, okay, ATP is just an ATP inside the cells, and then for the phosphocreatine, and then anaerobic metabolism, okay, is fast, right? Um, to have 2.5 times faster, but can only support 1 minute of maximal exercise. 1 minute maximal exercise means your full sprinting speed and stuff. Okay. Aerobic metabolism can support exercise for hours, so long jogs, etc. Okay. Okay. So low intensity. So when you're sitting around, you're burning energy, sugar and fat. You actually fat burns brighter. So you burn 1 gram of fat burns twice as many calories as 1 gram of sugar. You burn 60% of energy comes from fat, even though you burn less fat, and 40% from sugar. Okay. Um, and that's the same as you increase. But as you get past a certain limit, okay, you start not getting enough oxygen. When fat requires oxygen to burn, so you start burning less and less fat, and to compensate, you burn more and more and more sugar. Okay, so at 100% maximum intensity, you're only burning sugar, which is why for fat burning exercises, you're supposed to go, okay, right about here, okay, where you're maximally burning fat, okay. Just to make sure, okay. Hormones that increase during exercise: glucagon to release more sugar into your bloodstream, cortisol again to put more sugar in your bloodstream, catecholamines like adrenaline and norepinephrine to stimulate to increase heart rate, okay, and breathing rate, and growth hormones to again increase sugar levels, okay. So promotion of conversion of triglycerides to glycerol and fatty acids to burn, cortisol, catecholamines, growth hormone, conversion of sugar to raise glucose levels, glucagon, catecholamines. That's all. Okay, insulin secretion is suppressed during exercise. Okay, insulin usually drives sugar into your body cells of the body, but it doesn't want to do that now. Okay, it wants the muscles to get sugar. For the muscles to get sugar, to preferentially get sugar, the other cells don't. So you turn off insulin secretion. Okay, oxygen consumption is a measurement of cellular respiration. Post-exercise oxygen consumption is used to store ATP. Okay, myoglobin levels of oxygen. So your muscles contain something called myoglobin. Myoglobin is very similar to hemoglobin, okay, but it's found in muscle and it traps oxygen and holds it there. So it's an extra storage capacity for oxygen. Okay. Um, Several factors in exercise. Mitochondria are limited in number, so mitochondria are required to burn. They're required for the citric acid cycle and the electron transport chain. So not enough mitochondria, you're not burning any extra. Okay. Um, okay. Insufficient oxygen supply, so not breathing in enough oxygen, not having enough capillaries to get the oxygen in. Um, okay, will limit again sub-maximal exercise capacity, not maximal exercise capacity, because maximal exercise capacity, you're not using oxygen. Okay. Okay. So I want you guys to understand this thing called oxygen debt. Okay. This is oxygen debt. Okay. Or deficit. Okay. Okay. So when you exercise, the cellular energy use exceeds the oxygen intake. Okay. So you're burning your spare. So, okay. And then you suck in, okay. You have to repay that later. Okay. So oxygen debt. Okay, that's why you're still breathing in harder even after you finish exercising. Your breathing rate should return to normal, but it doesn't. Okay. Okay. So ventilation, so ventilatory responses to exercise, increased rate and depth of breathing. This is actually a feed forward signal. Okay. You're breathing harder even before your body needs it. And that is feed forward response. Okay. Okay. So proprioceptors in joints and mechanoreceptors in muscles also stimulates exercise hyperventilation. Okay. Okay. So you can see how much your respiratory rate increases. So this level 6, okay, maximum exercise, you're breathing in 40 liters per minute or more, and that's more than 7-fold approximately. Okay. Okay. So make sure you understand what a feed forward response is. Okay. So light gas is an exercise. Your arterial blood pressure, or sorry, your arterial partial pressure of oxygen should always roughly remain the same. Okay. Your arterial PCO2 should decrease. Okay. Your venous levels of O2 should decrease because you are using up more oxygen as you breathe. So the oxygen is being released more. So the venous levels are dropping, not the arterial. Okay? Because arterial you can always get from the air. Okay. Your arterial pH does decrease because when you are exercising, you are releasing more CO2. Okay, and CO2 causes it's going to be it's going to be carbonic acid in the blood, plus you're releasing lactic acid. So your pH will drop, and eventually at maximum exercise will plummet. Okay. Okay. Cardiac output increases dramatically during exercise. Cardiac output is determined by heart rate versus time stroke volume. Okay. I'm sure you guys knew that. But so heart rate goes up because your sympathetic response kicks in more. Your stroke volume goes up because there's more venous return and more force of contraction. Okay. But more force of contraction leads to more venous return anyway. Okay. Okay, so much bigger cardiac output. Okay, this is actually a really cool graphic and shows you exactly what happens. So you go from cardiac output being about 6 to about 26. So more than a fourfold increase. Okay, so the brain is about the same. Okay, 13% at rest and 3% in exercise is the same amount of blood. Okay, your brain really can't accommodate more blood because it's stuck in this big square or round box and you can't access more blood to. Okay, the heart is at 4% here and 4% there, but remember this is 4 times 4, so 4 times more blood. Okay, the kidney is less blood, right? The intestines is less blood. Your skin is actually a little bit more blood, just a little bit. Okay, 2.5% is times 4 is a little bit over 10%. So there's a little bit more blood going to the skin, but not very much. And your skin doesn't need a lot of blood, but it's driving it there primarily to cool it off. Okay, and look at this big change. So 21% of 21% of 6 liters is about a little bit over 1 liter. Okay, 88% of 25 liters is about 23 liters. Okay, so it goes from 1 liter to 23 liters of blood. So really, really, really big difference. Okay, all right, so let me make sure you share sound. I don't know why I can't play the music. Okay. Okay, so peripheral resistance decreases due to vasodilation in exercising muscle. Okay, and that causes that causes the arterial pressure to rise slightly. Okay, so sorry. Mean arterial pressure is cardiac output. Let me explain that here. So mean arterial pressure is equal to cardiac output times TPR, total peripheral resistance. Okay, so total peripheral resistance goes down, but cardiac output goes up much more than TPR goes down. So your mean arterial pressure goes up. Okay, and your systolic changes more than the diastolic. Okay. Okay. During exercise, blood pressure increases without activating homeostatic compensation. So usually, okay, your receptors have a response to increased blood pressure. When it increases blood pressure, it compensates and slows down your heart rate to decrease blood pressure and to bring back into homeostasis. Okay. But it doesn't for exercise. I think this is the most likely one of the 3 that's possible. Usually, probably due to H hydrogen increasing. Okay. Okay. So feed-forward responses to exercise. So a lot of changes occur in the absence of stimuli or before the stimuli are actually present, you don't feed forward. A good example is breathing. When your heart rate also increases before your blood actually needs it, etc., etc. Oh, okay. Temperature regulation, okay, is caused by so exercise. You generate heat. Um, Sweating, that's the evaporative cooling. The problem with that is dehydration of the blood volume. So you sweat out fluid, you're going to suffer from dehydration. Okay, increased cutaneous blood flow. So the blood flows that go to your skin and will be pushed off, but that causes again diversion of the blood from the muscles. Okay, um, okay, and that in heat stroke, in hot and humid conditions, hot conditions are obvious, but humid, it blocks the sweat from evaporating. If it blocks the sweat from evaporating, you don't get the evaporative cooling effect. Okay, and that can lead to heat stroke. Okay. Exercise and health. Exercises lowers the risk of cardiovascular disease. Okay, so let's take a look at why. Okay, so you see exercise, you're closer to normal. So the red is type 2 diabetes. If you exercise, then you're closer to normal. Okay, if you exercise, you're closer to normal. Okay. Okay. Moderate exercise enhances immunity. Okay. Um, okay. The reason for this is actually pretty simple. When you exercise, your body, your muscles increase something called glucose transporters in your muscle. These glucose transporters uptake glucose without insulin. That's the most important key, without insulin. So, okay, it responds without insulin. So it takes blood from your, or it takes sugar from your blood into your muscles without insulin. So your blood glucose levels are better. Okay. All right. Hopefully that makes sense to you guys. All right.